Now moving in to questions in which we have more than one spectrum to analyze. Love these ones. Chemists investigate an unknown compound X. They obtain information from a variety of sources. First of all, we've got X has got 61.2, 6.1, 32.7 oxygen. So from that, we can get the empirical formula, which is C5H6O2. Okay. Not going to dwell on the empirical formulas, but essentially get the percent, turn it into grams in 100 grams, turn those to moles, get the ratio if needed. Here is fairly obvious, 5 to 6 to 2. So that tells us the mass of the empirical formula is 98. Now that means the molar mass is either going to be 98 or it's going to be twice that at 196 or 3 times that at 294 and so on. When we look at the mass spectrum though, the highest peak that we see on the mass spectrum is 98. So that tells us that the empirical formula and the molecular formula are the same thing. Okay, if the empirical formula was half of the molecular formula, in other words, if the molecular formula was C10H12O4 with a mass of 196, you'd have more peaks past the 98. Now, once we got this molecular formula, oxygens don't affect the number of hydrogens at all. 5 carbons should have 5 times 2 plus 2 or 12 hydrogens. As there's only 6 hydrogens, we're short 6 hydrogens, so we have 3 degrees of unsaturation. So we already know the molecular formula, we already know 3 degrees of unsaturation. When solid sodium carbonate added to an aqueous solution, effervescence is observed, right? That tells us that it's an acid. There are 5 peaks in the carbon-13 NMR spectrum. In other words, we have 5 different types of carbons. So all of these 5 carbons are different. 1 mole of X reacts completely with 320 grams of bromine in the dark. Well, 320 grams of bromine is 2 moles of bromine, so that's 2 carbon-carbon double bonds. So remember, we had 3 degrees of unsaturation. 1 of those is the carbon-oxygen double bond in the acid, and the other 2 come from carbon-carbon double bonds. In other words, there's not a ring in this compound. All the degrees of unsaturation are due to double bonds. Okay? So now can we put things together to get the structure? Well, we know we've got an acid group. We know we've got 2 double bonds in there, and the double bonds, one of those carbons can't be the same as another one. So pretty much it has to be this structure. Acid group, 1 double bond, another double bond. All kinds of information in this question. We'll take it bit by bit. Compound C, compound of carbon, hydrogen, bromine only. Bromine's got 2 isotopes, equal abundance. Use all the information below to get the structure, given our reasoning. Well, first of all, we've got enough information to get the empirical formula. Percent to mass, to moles, to ratio. Empirical formula, therefore, is C3H5Br. Now, the mass spectrum of C contains peaks at 15, 41, and a pair of peaks at 120 and 122. Now, you see that pair of peaks, and they're going to be equal abundance, one assumes. That's because you've got a bromine in there. So these peaks have got a bromine in them. These ones do not. When we look at the empirical formula, we've got C3H5, which weighs 41, plus bromine. So there's the peak of 41, okay? And then here are the peaks at 120 and 122. 15, of course, is CH3. And therefore, here are the other assignments. So in other words, we've got to have a fragmentation pattern that allows us to have CH3. We have to have a fragmentation pattern where we lose the bromine. Well, that's not too tough. And then, of course, here's the indicator of the bromine, nicely right there. And because this is the highest peak, we assume that tells us that it's not just the empirical formula, the C5H5Br, but the molecular formula is C3H5Br as well. Next bit of information is the degree of unsaturation, which we can get from the molecular formula. 3 carbons should have 8 hydrogens. Okay, well, of course, a hydrogen, and the bromine counts as a hydrogen. So we're actually short 2 hydrogens, which means there is 1 degree of unsaturation in this. The infrared spectrum has absorptions at 550, 1630 and 1330. Well, let's compare that to our data sheet here. 550 is probably the CBR. 1630 as probably the unsaturated, the C double bond C, and 3030, well, that's going to be carbon hydrogen. Okay, so we have an alkene in there. We have a carbon bonded to a bromine. We've got 3 carbons, so there's 1 other carbon left, and we know that that 1 carbon has to be a methyl group. So putting all that together then, there's the methyl group, there's the double bond, there's the methyl group, there's the double bond. The bromine has to be attached to 1 of the carbons of the double bond because it can't be attached to the methyl group. So it's either going to be 2-bromo propene or 1-bromo propene. Finally, compound C is a Z isomer. Well, you only have E or Z isomers when both carbons in the double bond have different things on them. In this 2-bromopropene, carbon 1 has 2 hydrogens. In 1-bromopropene, carbon 1 has a hydrogen and a bromine, carbon 2 has a methyl and a hydrogen. So that tells us it cannot be the 2-bromopropene. It has to be the Z isomer of the 1-bromopropene. Gosh, I love these. So I should probably have put this one first in this group. Spectra give much information about the structure of organic compounds. Duh, no poop, Sherlock. The mass spectrum and the infrared spectrum of ethanol are shown. So it can be deduced by the presence of the peak at 46 in the spectrum. There's that peak right there. Well, the molecular mass of ethanol is 46, so that is the molecular ion C2H5OH+. What can be deduced by the presence of the peak at 15? There it is down there. Again, A-level people make such a big deal about these little nubbins at 15. They're so small that, you know, they're almost background. But anyway, let's live with it. 15 is the CH3+. And what can be deduced by the presence of absorption 3100, 3500. That's that beautiful, symmetric, pretty peak there. That is, of course, an OH stretch. Compound Y is a halogenoalkane, simplified version of the R spectrum. The mass spectrum, COM13, low res, high proton NMR of Y are shown. Use these to determine the identity of Y. You must use evidence from each spectrum and explain how you used it. So looking at the IR first of all, what can we get? Well, there's this lovely peak here at about 650. So that would imply that our halogen is a chlorine. And then this big sharp peak here is CH. So let's look at the mass spec. First thing is we got a peak at 35 and a peak at 37. Peak at 37 is 2 squares. The peak at 35 is 6 squares, so a 1-to-3 ratio. That's a pretty good confirmation that the halogen that we've got is Cl. Now up the other end of the spectrum, we got 3 peaks here at 128, 130, and 132. That are nicely indicative of 2 chlorines. We've got the 9-to-6-to-1 relationship. There's the 1, there's the 6, there's the 9. We derived that earlier on. The 126 peak is where both of the chlorines are chlorine 35, and then of course you've got the rest of the molecule. The 128 peak is where one is 35, one is 37, and the rest of the molecule. And then the peak at 130, both of the chlorines are 37 plus the rest of the molecule. That would indicate that the rest of the molecule has a mass of 56. Now, we're done with the chlorines. We got 2 chlorines in there. So this must just be hydrogens and carbons. So it can't be any more than 4 carbons because 5 carbons weighs 60. And it can't be 3 carbons because then that would be 3 carbons and 20 hydrogens. So this rest of the molecule must be 4 carbons for 48, and then 56 minus 48 is 8. So 8 hydrogens. This tells us that the molecular formula is C4H8Cl2. Now, 4 carbons requires 10 hydrogens to be saturated. Chlorine, of course, counts as a hydrogen, so there's the 10. So it is a saturated molecule. Okay, so already at this point, we know the molecular formula. We know there's no rings, there's no double bonds. It is just form of dichlorobutane. And there are 6 isomers of dichlorobutane. The 1,1, the 1,2, the 1,3, the 1,4, the 2,2, and the 2,3. Now I've assigned, using pretty little color coding, the different types of carbons that we have in this. Okay, if we look, for example, at the 1,1-dichlorobutane, carbon 1 has 2 chlorines on it, so it's different from anything else, and then 2, 3, and 4 are respectively getting further away from the 2 chlorine ones, so there's 4 different types of carbon here. Same thing with this. Carbon 1 and carbon 2 both have chlorines, but they're different because carbon 1 has 2 hydrogens, carbon 2 only has 1 hydrogen, and then carbon 3, carbon 4, you can see are different. Okay, again, 4 types of carbon there, 4 types of carbon there. You kind of expect there to be 4 types of carbon. However, if we look at these ones, we've got the 1,4-dichloro and the 2,3-dichloro, then we can see that here the symmetry of the molecule is such that there's only 2 types of carbons. So before I even reveal the carbon NMR, it's either going to have 4 peaks or 2 peaks, and that will enable us to eliminate a significant fraction of the possibilities. There it is there. 2 different environments, thus 2 different types of carbon. So we can cross out the 1,1, we can cross out the 1,2, we can cross out the 1,3. The 1,4 looks good, 2 different types of carbon, the red and the blue. The 2,2 cross out, and the 2,3 again, 2 different types of carbon. So we've gone from 6 possibilities to 2 possibilities. Now let's look at the proton. In the proton, what we see is we've got 2 equal abundance types of hydrogens, so 2 environments of equal size. Now, seeing as how we got 8 hydrogens, we're going to have, this is due to 4 hydrogens, and this is due to 4 hydrogens. So when we look at now color coding the hydrogens in there, the 1,4-dichloro has got the 2 hydrogens on each of the N carbons are the same, so that's going to be 4 of them, and then the carbon 2 and carbon 3 hydrogens will each again be the same. So we've got 4 and 4, so that looks pretty good. When we get down here to the 2,3-dichloro, well then the hydrogens on the chlorine carbons, there's only 2 of them. That would presumably, of course, be the further downfield one, the hydrogens on the chlorine carbons, but then there would be 6 identical ones otherwise. So here we would see 2 and 6, here we would see 4, 4. Thus we can eliminate the 2, 3, leaving us with the answer is the 1,4-dichloro, and presumably this peak here is the red protons because you've got the chlorine there sucking electrons away, and this will be the blue protons.